Hello, I hope you're doing really good and getting used to online lab assignments. Well, this week we will be working on Lab 9, Rotational Inertia. So in this video, I will go over the theory and also walk you through the experimental procedure. And I hope that will help you to complete the lab assignment successfully. Well, first, let's look at what is the rotational motion equation and the linear motion equation. So I believe all of you are familiar with Newton's second law, where we can analyze the linear motion, right? So the summation of forces are equal to mass times the acceleration. So here, A is the linear acceleration and F is the summation of F, that's the net force acting on the system, right? That equal to mass times the linear acceleration of the system. Well, when you think about the rotational motion, you can compare these two equations, kind of the same, right? So instead of summation of F, we have the summation of tau equal to, instead of M, I have I here, and instead of A, I have alpha. So here in this equation, the Newton's second law, A represents the linear acceleration. On this equation, alpha is the angular acceleration. Right, so you see the analogy here. So linear to rotational. So instead of linear acceleration, I have angular acceleration. And then this tau represents the net torque. It's not the force, because in order to rotation to happen, you need to apply a force dispersed from the center of rotation, right? So it's not just the force create the rotation. There should be a torque to create a torque. Sorry, to create a rotational motion. Then instead of M, here I have I, that I is the resistance to change the rotational motion. That's called the moment of inertia or a rotational inertia. Then here the mass is the resistance to change the linear motion, right? So if you have a heavy mass, it's hard to move linearly. Here, if we have a higher rotational inertia, then it's hard to rotate. Right? Then this I is the interesting factor here, or a new factor. So you can calculate I by taking the summation of mass times the radius to the power 2 of each chunk of mass. Right? So if you think about a big object like a disc or a long rod, then you need to divide this element into tiny mass pieces, and then you have to calculate this product, mass and the radius to the power 2 for each segment. So it can be done using mathematical equations, but we are in this lab, we are not going to do that, but we will be using the given equations. Well, so if you were in the real lab, you will be given with a Pasco interface, and then a rotary motion sensor, a hub, and a rod with two masses, and a disc and a hub, right? So experimentally, what we are doing is we screw one of these elements at one at a time. So first just the rod, then rod with two masses, and then the disc and the hoop. So we will attach these elements over here by the hub, and then we'll there's a thread that attached to the around this hoop. So when you apply a force along this string, we can rotate this hub around the central axis, right? So here the hanging mass is 20 grams. So let's think about, we are attaching a disc here. So this is the disc, and here's the string that attached to the hub here, and 20-gram mass is hanging from there. So when you let it go, the hanging mass will drop down under the gravity, and then it will rotate the hub over here, and that will eventually rotate the disc, right? So when it's falling, we can measure the angular velocity over the time of this hub. All right, so as I mentioned, we can measure the angular velocity. So if we can create a graph between angular velocity and time. So basically the graph of angular velocity versus the time. And here it is angular velocity over time, right? So if you calculate the slope means the rise over run of this graph. So it's going to be change in the angular velocity divided by time. So, you know, like change in velocity, that's the acceleration, and this is angular. So it's going to be angular acceleration. So simply we can take the slope of this graph and calculate the, no, you don't need to calculate anything, but if you calculate the slope of this graph, it will give you the angular acceleration of this object. Well, as I mentioned, so in the part 1 of the experiment, we will be using a rod with 2 point masses. Really, these are not point masses. As you see, it's a little bit distributed, but within our uncertainty, we can imagine or assume these are point masses. So basically, in the part 1 of the experiment, we are using a rod with 2 masses attached to that, and let it drop and measure the angular velocity versus time graph. Then we will be using just the rod. We will remove these 2 masses and let the just the rod to be rotated, and again collect the data for angular velocity versus the time. Then in the part 2 of the experiment, we will be doing a disk only. So we are attaching just the disk and let it drop, and then measure the angular velocity versus the time graph. And in the last step, we will be adding a hoop into the disk. So it is a combination of a disk and the hoop, and then we'll let it go. Again, remember, we are only using 20-gram mass here, and let it drop, and we measure again the angular velocity versus the time graph. So in the data that we provided, you should be able to see 4 graphs for each setup with angular velocity versus the time graph, and also the slope is indicated clearly. So you may use those data when you are completing your lab report. Well, let's look at the theory. So here, as you see, a mass is dropping down, right? No matter what is attached to the hub here, the small mass, 20-gram mass, is falling down. So if you think about this mass, it's moving straight down. Let's assume that it's moving straight down. However, in experimentally, it might be oscillating when you let it go. Just imagine, like if you attach a mass and let it go freely, it will oscillate around, right? So, but we can just ignore that, but it will add some experimental uncertainty. So that's one error factor that affect the experiment. Anyway, just assume that the weight is falling straight down, and here we can apply F equal ma, because this mass is linearly moving downward, right? So we can apply Newton's second law, F equal ma downward. Now we need to know what are the forces acting on this mass. So we know, like, weight of the object acts downward, which is m times gravity, mass times gravity, the weight of this hanging mass. And then it is attached to a rope, right? So there should be a tension acts upward. However, the weight is heavier than the tension, so it's accelerating downward. Well, so let's apply F equal ma downward. So we get mg minus t is equal to mass times the linear acceleration, the acceleration of this hanging mass. Then also we can apply torque equal r cross f for the hub here. In that case, we need to know what is the force applied by the hub and what is the radius, right? So basically, let's look at from the top of this. When we remove this disk, we should be able to see a picture like this one. So that's the center of rotation, and this is the hub that I mentioned. So from the center to this hub is 1.5 centimeters, and this string is attached to the hub over here. So the force is acting along the string here. Whatever the tension force is the force that applied, and this is the radius. So that force is creating a torque around this hub, right? So we should be able to calculate that because we know the distance, the radius, and the force acting on it. So here, torque is R cross F. So, you know, like it's cross product, it will be R times f times sine value of the angle between r and f. Here r and f are perpendicular to each other. R is that one and f is applied along the tangential line. So they are perpendicular to each other. So the angle is 90 degree, right? So we can get rid of this cross product by taking r f sine 90. You know, sine 90 is 1. So we can simply write that the torque is r times the tension of the rope, right? And remember, this r is 1.5 centimeters. Well, also we know that the torque is I times alpha. I is the rotational inertia, alpha is the angular acceleration. Now these two equations are equal to each other, right? So we can maybe we can equal these two and simplify it. So the tension times r is equal to rotational inertia times the angular acceleration. Also, I know t little better, right? Because I can express t in terms of mg and ma using this equation. So t is mg minus a times r. Mg minus ma is the tension. So I time it by r. That's equal to I times alpha. Let's keep simplifying this. And a is r alpha. Linear acceleration is equal to the radius times the angular acceleration. So times r is equal to I alpha. And then I can simplify it a little bit further. So I need the answer for I, right? So I is equal to m times g minus r alpha times r divided by alpha. So here I see two pieces. So I can simplify it a little further. So mg times r divided by alpha minus m times alpha will cross multiply. So it will be mr to the power 2, right? So the theoretical equation for rotational inertia for this system is mgr over alpha minus mr square. So using this equation, we should be able to calculate the moment of inertia. Now, do we know m? This m is the hanging mass, so it is 20 grams. And g, that's the gravitational acceleration. So in this lab, we're going to use the gravitational acceleration as 980 centimeters per square seconds, right? So centimeters per second square, 980 centimeters per second square. That's the gravitational acceleration. And r is 1.5 centimeters. Again, m is the hanging mass. Remember, it is not the mass of the hoop or the rod or anything. It is just m, that is the hanging mass, which is 20 grams. And r, again, 1.5 centimeters. And alpha, how do we know alpha? Remember the graph, angular velocity versus time graph? So that's the slope of the graph, right? So alpha is the slope of angular velocity versus time graph. So once you know this value, you may calculate I. So basically, this is the answer for the question number 1, where you have to derive the equation for I. So you better understand this and derive equation by yourself. Well, then in the question 2, it's asking you to calculate the experimental moment of inertia or the rotational inertia. In that case, you may use this equation. So let's do an example calculation. I'm not going to solve it for you, but I'll tell you like what to do. So here, let's say I want to calculate the experimental rotational inertia for the rod with point mass. So here, this is the equation, and mass is 20 grams because that is the hanging mass. Then the gravitational acceleration is 980 centimeters per second squared. And the radius is 1.5 centimeters. Here, oh, this should be alpha. So alpha, not A, my apology, it's not A, it's alpha, is the slope of the graph for rod with the point mass. So if you look at the given data, you will see the slope of that graph is 0.528. So this alpha going to be 0.528. You may plug these numbers and solve for I. So in my calculation, my answer was 55,636 grams per centimeter squared. Remember, it's gram per centimeter squared. Here we're going to use grams and centimeters in our calculations. Well, then in the question 4, it's asking you to calculate the theoretical values. So in that case, you can use the theoretical equation to calculate this. So the for a hoop, the moment of inertia can be calculated using this equation, where m is the mass of the hoop or the ring, then r1 is the internal radius, inner radius, and r2 is the outer radius. So you're measuring it from the center to this corner, and then for a point mass, we can use this equation, which is m r to the power 2. M is the mass of this point mass, and the r is the distance from the center or the rotational axis to the mass. And remember, in the experiment, we use 2 point masses. So when you're calculating the moment of inertia for the point masses, it should be twice as this one. Okay, so then you can think about the errors that could happen in this experiment. So one, I already mentioned, that's the oscillation of the dropping mass. So we assume that it is going straight down, but it is not. It's really little wiggly. I will share the data with you so you can understand it a little better. So let me share the data set that I'm going to send it to you. So here, as I mentioned, the first graph shows you the graph of angular velocity versus time for the rod only. Likewise, right? So this one is the graph for the rod plus the point masses. Now, this is where I want to go. So on this graph, you see this is the fitted line, but the real data is really not a straight line. It's going a little bit curved, right? So it's due to that oscillation. Then the other error factor may be the friction. Remember, like we assumed that the system attached to a rope, and we didn't care about the friction that's act over there. So maybe there's a friction acting on the those slopes, I mean the rings, because in a real system, the friction is there, right? So in the physics world, we assume that we can neglect the friction, but the friction is still there. So this is the picture that I'm referring to. This picture. So this string and the hub over here and the pulley, there's friction acting on it, but we just ignore that. So that will add a error factor into our calculation. Well, I hope this will help you to complete the lab report successfully. And if you still have questions, please join a Zoom meeting and get help from a TA. Thank you, and I'll see you next week.